You have been looking for a tool for automated system-level testing of railway components, whether to test the real hardware or the software itself in a virtual environment? Look no further. With CANoe, you have found the ideal solution. Dive in and see the possibilities that the Vector tool can offer to you. Hi, my name is Mario, and I'm the product manager for our railway signaling add-on. This add-on adds support for railway-specific communication protocols to our system-level test tool CANoe. In this session, I want to give you an overview of the tool on the example of explorative and automated testing of an object controller of a point. In railway signaling, such object controllers act as the interface between the digital interlocking and the field element next to the track, such as points and light signals. The object controller translates Ethernet-based communication from the interlocking into proprietary communication used by the field elements. For the former, the European Committee ULinks has specified the protocol SCI, which is loosely based on the German predecessor NeuPro. For the latter, digital I/Os or CAN network communication are commonly used. The object controller that I have here with me, the PSS rail by the company PILS, uses the protocol SCI based on ULinks to communicate with the interlocking and digital communication to exchange information with the point motor. Keep in mind that the tool CANoe can be used for much more than the testing of object controllers, with support for other Ethernet protocols such as OPC UA, TRDP, MQTT, EtherCAT and Profinet, and other bus systems such as CAN, CANopen and Profibus, as well as analog, digital and serial I/Os. CANoe can be used for testing of a wide range of applications. Enough about that, let's dive into the tool. Here we can see the graphical user interface of CANoe. There are some pre-built panels that I have created and some windows that are natively integrated into CANoe. Let's start with the panel at the top left, the one for the electronic interlocking. This is one that I have created. It has a point display, which displays the position of the point as reported by the object controller to the electronic interlocking, as well as some control elements to open the connection on raster and PDI level, as well as the possibility to send the command to move the point to the left or right position. Also, in LEDs, I visualize the connection state of the raster as well as the PDI layer. Finally, I have some LEDs that display when STI telegrams are being sent and when they are received. The next panel is the panel for the object controller of the point. Here you can see that I can switch between SIL and HIL testing. In SIL testing, the only option I have is to run the executable. This executable consists of the application code of the point object controller, as well as the possibility to communicate with CANoe. The other panel I have here is the panel for the point motor. It offers the same visualization of inputs and outputs, in this case digital I/O. You can see 6 LEDs. This corresponds to the 6 wires that we have here at the PSS rail. There are 3 inputs of the object controller, the outputs of the point motor. Those are whether the point is currently in left position, in right position, and whether or not it is able to move, as well as the inputs of the point motor, so the outputs of the object controller. Those are commands, so they are a high voltage level, when the point is supposed to move into left position, move into right position, and to set the main relay. Also I have the possibility to slightly adapt the behavior of the point motor. In this case, I can only change the time it takes for the point to move. Additionally, I could also do more fault injection, like simulate trail behavior of the point. But for this demo, I want to focus on the time that it takes the point to move. Lastly, I have a simple image that displays the current position of the point. On the right side, there is the graphics window. It displays the state of the inputs and outputs, so the voltage level on the wires of the point motor. You can see this later when the measurement is running. At the bottom left, there is the trace window. In the trace window, I can see all of the events, all of the variable changes that happen in variables within CANoe. Luckily, I can filter these out and only display whatever I currently need. The final window is the window for automated tests, of which I have 2 currently. Both are functional tests, and they only test whether the point is corresponding or responding directly and correctly to the command to move the point. We will see these later. On the second desktop within CANoe, I have the communication setup window as well as the simulation setup window. Let's start with the simulation setup window. Here I have two nodes for the point and the electronic interlocking within the Ethernet network. I have two Ethernet networks, as you can see, Ethernet 1 and Ethernet 2. This is because I have redundant communication over two wires. You can see here the blue and the gray one that live in two different Ethernet networks, just to make the communication even more secure. Within the simulation setup, I can set the TCP and IP stack settings, so IP addresses, MAC addresses, and so on. In the communication setup window, we see application models as well as data sources. You can think of the data sources as header files and the application models as source files. So within the data sources, I can declare variables and methods while they are implemented in the application models. So let's start the measurement and see what the tool looks like in action. You can immediately see that some panel elements have disappeared. This is because I have switched to SIL testing currently from this panel. In SIL testing, we do not care about whether there is a connection. We don't care about the transport protocol logic itself. We only care about the application logic. In this case, the application logic is sending and receiving of the commands and not more than that. So we don't care about whether we can open, close a connection, and we therefore also do not care about connection states. If I switch to HIL, which I will do just for now quickly, you can see these panel elements appear. But let's do SIL testing first, as you would also do during development. What I need to do first is run the executable. As I've said earlier, this executable consists of the application logic of the object controller, as well as the possibility to communicate with CANoe. So if I run this, the executable is being started. I just quickly change the size of the window and keep this on top. I will move it over the window for automated tests because we are not looking at them for now. You can see that when I started the system under test, we got the feedback where the point is currently. We have set this when starting the measurement. So the point motor is currently in right position and the point is able to move. This is what the system under test detected when it read the inputs and then sent the according SCI telegram to the electronic interlocking. Well, when I say SCI telegram, I mean basically only the byte structure, rather than the complete layer, including raster and TCP IP and so on. So what can I do now with my panels? I can trigger movement to the left position. And what you can see is that the LEDs have lit up. Also, we can see what happens with on the wires. Well, currently not on the wires because we don't test the actual PSS rail, but we can see what the output is, what the variable is set to. If I now move the point back to the right position, you can once again see and pay attention what the outputs are. So we're sending a command move point and we're receiving a message point position. And because I'm now moving the point to the right position, we should see this LED light up as well as the main relay. The is left output should be low. And then after a certain time, the is right output should be high. So I will do that and pay attention. So what I've just predicted exactly happened. So our system under test runs perfectly fine. And rather than clicking on buttons, we can also do automated testing. You can see that the first test case was not done because the point was already in the position where it was supposed to end up in. Because now it is in left position, I can run these tests again, and both tests are actually being executed, and we can see the result. Both tests pass. Let's look into the test report. I will close the system under test for now and just stop the execution. So what can we see? We see that we expected the receipt of two message point positions. One with the information or the payload not in end position and one with the intended position. We can see here that we compare the fields of the SCI telegram, which consists of protocol type, message type, sender and receiver ID, as well as the point position. Point position 0x03 corresponds to not in end position, and 0x02 corresponds to the right position, to the left position, sorry. For the other test case, right, we can see that the payload is 0x01 for the actually right position. Now that we have confirmed that the software is running with software-in-the-loop testing, we can switch to hardware-in-the-loop testing. I would just simply change this within this panel, and as before, you can see that the panel elements appear. Currently, the connection is not opened because the PSS rail is not even powered on. So I will supply it with power, and you can see on the VT system that power is supplied and current is being drawn by the PSS rail. You can also see the LEDs here light up. So it's currently booting. Because the PSS rail is configured in a way that it sends the raster connection request and the electronic interlocking, which is simulated in CANoe, then replies with the connection response, we need to first open the connection on the electronic interlocking to allow the receipt of this connection request. So I will do that. I will connect raster, and as soon as the PSS rail has finished booting, it will send the connection request. We will see this appear in the trace window. There it is. We can see within the receive monitor, so we've received this message. It's a connection request message. And if we open this, we can see the actual content of the header, as well as the protocol version if we were interested in it. Because these numbers might look meaningless to you, we can switch to hexadecimal and see that this is the protocol version 0303. Now that the connection is opened on raster layer, we can also open the connection on PDI layer. Here we can see that the handshake has taken place. Everything, by the way, is running on these two cables still because we are based on Ethernet connection. We can see that there are some SCI telegrams which belong to the handshake. We can see the current status as raster and PDI are connected. We can also now see the position of the point motor because during the handshake, this information is exchanged from the object controller with the electronic interlocking in status telegrams. I can now use exactly the same panels and panel elements to trigger a movement. Now, instead of just checking the value in variables, I actually measure the voltage on these cables and set the actual voltage from the VT system. So now I do real hardware testing. Once again, I can move this back. I can also change the time it takes the point to move. So with 1 second, we should now see that these blocks become sharper or have shorter distances between the command being sent and the position to actually change. Now we can do exactly the same automated tests as in the SIL testing because the requirements have not changed. It's still the same case that when we send the command move point, we expect the point to not be in end position anymore and then to be in the desired position. So I can run exactly the same test cases and you can see both of them pass. The only difference here being that it took a much shorter time for the tests to pass because the point is now moving quicker because I've changed it in the panel. I hope that I could give you an overview of the capabilities of our test tool for the explorative and automated testing of railway components. Once again, I'd like to stress that the tool is not limited to testing object controllers. A big thank you to Pils for providing the PSS Rail object controller. In the video description, you can find more videos from the Vector Railway Engineering Day. Enjoy the videos and also check out the successful case studies we have on our website. Go ahead, dive in and discover.